Here we're going to walk through the Grignard reaction, or the lab basics setup for the Grignard reaction. In this case, what we're going to do is make malachite green because it's cool and colorful. And because it is colorful, one of the things we can take advantage of is we can determine the yield via absorbance, which is a little bit different than how we've done it in the past because you're using an absorbance to determine the amount of product made, not a balance. So it's a little bit of a challenge or a twist on this. So first off, our Grignard chemistry, kind of our standard stuff, it was developed by Victor Grignard. And what makes it really special is that it gives us a nucleophilic carbon. And in particular, we would then use that nucleophilic carbon for nucleophilic addition. Why is it so special to have nucleophilic carbons? Well, carbon is typically not nucleophilic. Remember, a nucleophile is an electron donor. And because it donates electrons, it has to somehow maintain them. Carbon is too low in electronegativity and is too small to really stabilize those electrons well. And so most of our reactions that produced nucleophilic carbons end up getting names associated with them. And Victor Grignard is no different. So we end up with the Grignard reagent, which is this last piece out here. And, sorry, I thought I misspelled. Grignard is the one that developed that. And really kind of the idea behind this mechanism is that we would use elemental magnesium. And what makes elemental magnesium so special is that it has those pair of electrons, okay, that it doesn't really want because magnesium would like to transition to magnesium plus 2. Okay, so to do so, what it will do is give up a single electron. Okay, so we're running a radical mechanism. That single electron can pair up with our bromine. We can get another, or not another, but that sigma bond breaks, giving us the, of course I drew the wrong color one here, giving us our radical phenyl group in this case. And then we would still have that leftover, or a single leftover electron from the magnesium, which could then pair up and form that sigma bond, that new sigma bond that connects it. That sigma bond in and of itself is not a particularly stable one because it is an ionic bond. We're looking at the connection between a metal and a nonmetal with the carbon. That magnesium holds a typical +2 charge. The bromide connected to it is a -1, which means our carbon comes out of this with a -1. And that's where we're seeing the nucleophilic carbon. Okay, so in your particular classes or experiences, one of the things that may be helpful to go through and do when you think about the Grignard is, instead of seeing all the metal out there, is immediately kind of delete the metal from the structure and recognize you're looking at that negative carbon. Okay, what we just walked through here is what's known as the set mechanism, or single electron transfer. Why we don't just call it radical, I don't know, but that's where we're at. Okay? And that's how we get our Grignard. Once we have the Grignard, we can now react this with polar pi bonds. Okay? And there's some limitations behind the Grignard reagent, and one of them is that we need to do a polar pi bond reaction. Our classic polar pi bond is looking at a carbonyl, and in particular with Grignards, we really aren't super concerned about what's out here. There are some exceptions to that, but for the most part, we don't really care what those R groups are. As long as they're carbon or hydrogen, we're usually okay. And what ends up happening is, because we have this resonance option, we can end up forming a very electrophilic carbon. Okay? And that electrophilic carbon is now what is susceptible to the Grignard reagent. And the Grignard reagent can now launch a nucleophilic attack. Okay? So if we look at the general form of a nucleophilic addition reaction, we start with the nucleophilic addition. We know it's an addition because we end up breaking the pi bond, and we've added a nucleophile. That's then followed in this case by an acid-base reaction. That acid-base reaction is to neutralize that negatively charged oxygen. One thing to note here is that this says 2 in front of it. That isn't a 2 for equivalence. That's the number of steps. The acid-base reaction has to happen after our nucleophilic addition has happened with the Grignard. And that has a lot to do with the reactivity of the Grignard reagent. We have a negative carbon electron donor. If you throw in an acid, it's going to do an acid-base reaction and quench the nucleophile before we actually get our nucleophilic addition reaction. Which kind of gets us to this next part, okay? Looking at our carbon nucleophile. We want to really limit the presence of any acids, okay? And the reason for that is that this nucleophile is an electron donor. And if we think back to our definitions, an electron donor, well, bases are also electron donors. By accepting H+, they had to donate electrons. So a carbon nucleophile is a base, okay, or has the potential to be a base, which means we have to be very, very careful to limit the presence of acids. Why is that particularly challenging for us? Well, for our semester, usually we're in the fall. And in the fall in Arizona, we have to worry about monsoons. And if it tends to be raining outside, the presence of water in the atmosphere is enough to react with the Grignard reagent and quench the Grignard reagent before we actually get it to do what we want it to do. So one of our big kind of precautions with these Grignard reagents is to make sure that our glassware is extra, extra dry, and that all of our chemicals, as best as possible, have limited exposure to be able to absorb water from the atmosphere. Okay? There are cases where we just fully expect it to fail in undergraduate labs. Like if we lived in a humid environment, it's not expected to really perform. So one of the things that I like about this version of the experiment is we are running it in an inert atmosphere, and while you don't get to do that under an atmosphere experiment, you do at least get to see some of the aspects on how we've rigged it up. Okay? So we do have to be concerned about that acid characteristics and the next part, secondary nucleophiles. Oops, that's not right. Secondary electrophiles. Okay? When we want our nucleophile to react, we want it to react with an electrophile. If our molecule has another electrophile present, well, now our Grignard's going to be competing for two different sites, and it can result in a mess of different products. So we've got two structures kind of shown below to help kind of emphasize the issues behind these. If we think back to our Grignard reagent, the Grignard reagent relied on kind of the polarization of a carbon-bromine bond. So we could see that halide and be like, that's the spot where I'm going to make a nucleophilic carbon, okay, a few steps in. But in that same molecule, I also have that hydrogen. And you might say, well, an alcohol isn't that acidic. Neither is water, okay? The acidity of alcohols and water is high enough, or really that the basicity of this carbon Grignard reagent is so strong, it will easily deprotonate those hydrogens. And you should be able to see that by drawing out a basic acid or a simple acid-base reaction and deciding which is more stable, a negative carbon or the negative oxygen. Okay, so we have ways that we can explain that that's not going to be a good Grignard reagent because it has internal acids present. If we shift over to the other structure, this would be an example of our potential electrophile. Okay, why would this work for our electrophile? We have that electrophilic carbonyl, that polar pi bond. Okay, unfortunately, this same molecule also has an acidic hydrogen, which means if we tried to use this as an electrophile, probably all we're going to end up with is the Grignard reagent neutralized by the acidic hydrogen. Okay? So that acid-base reaction happens much, much faster than our nucleophilic addition. So make sure you look at your reagents carefully and ensure you don't have any kind of secondary electrophiles or acids floating around in your molecule. The other part that makes this experiment kind of fun is that we make Malachite Green. Okay? Some of the other Grignard standard labs do involve other things that are interesting or potentially interesting, but I like the idea of this color. And so what we end up going through and doing is making Malachite Green. Okay? Malachite Green is extra cool because it is colorful. And it is colorful because of the conjugation of these pi bonds. This nitrogen can donate electrons in, and if we look, we get tons of resonance options. Those electrons could have come back, okay, kicking that around and back, and we could have gone out this direction, okay? And it's all of those resonance compositions that end up shrinking the HOMO-LUMO gap, which probably just triggered half the class. That HOMO-LUMO gap now changes or shrinks a little bit so that the energy required to jump from our highest occupied molecular orbital to our lowest unoccupied molecular orbital now happens to fall in the visible range. Okay, so if we were to look at kind of an image, we've got a very crude molecular orbital diagram. Okay, so these are our molecular orbitals. Light can come in and cause that electron to jump to a higher energy state. Okay, that would be the absorbance. So what's happening in the case of malachite green is it is absorbing all the purple light. Okay, since purple light's now being absorbed, we don't see that, and the resulting color that comes out is green. Okay, that excited state can potentially relax back down, which means the emission of light. This molecule does not relax back down with the formation of light. It does it thermally and energetically, so we won't see anything fancy there. But all we really see is that color. Why does this become extra kind of cool as a secondary thing for this lab? Well, this light we can monitor through a piece of equipment. We can use a UV vis spectrometer to look at the light and tell how much light was absorbed. If we layer in what we learned back in 152 or 151, we've got Beer's law, where we've got the absorbance is equal to, should have looked it up, our path length times our concentration times the extinction coefficient. Okay, why is that cool? Well, I now have a direct way where I can look at the absorbance readout from my instrument, and I can tie that to the path length or to the concentration of my sample. So this would allow me to now determine through concentrations how much malachite green was produced. This is kind of neat because now I don't have to isolate malachite green. I can leave it in the reaction mixture, assuming there's no other secondary molecules that absorb light at that wavelength, which could be a reasonable assumption. Could also be a bad one. Okay, this does require a balance of knowing standard concentrations so that we know the extinction coefficient and we know the path length. So it's going to involve some drawing out of some plots, but it would allow us to simply quote unquote to determine the concentration and ultimately yield of our final product, which is kind of neat. DeGassing. Okay, so when we're looking at this next system, remember I said we needed an inert atmosphere. So what's happening or about to happen is that dry nitrogen is being flowed through the apparatus. That's going to build up a pressure of nitrogen, so we need to remove that pressure because we don't want effectively a bomb for a reaction. So we'll remove the nitrogen source, we'll squeeze the balloon, that'll push air back out through the bleed hole, and we repeat this cycle multiple times. The idea being that if any water happened to make it in through our initial building of the equipment, that we would now degas or remove all of that water and some secondary other potential molecules that could lead to issues, and we would now have an inert nitrogen atmosphere where we're not going to have any problems. So that's what we're seeing here in this next section. Solvent transfer. Most open bottles absorb water, and THF is no exception. In fact, THF, the solvent that we're using for this experiment, is readily miscible with water, which means it will absorb water the instant we open it. So the easiest way to do this is to make sure your bottle stays closed. Always. But if it's always closed, how do you get the liquid out of it? Okay, and that then becomes the process that we're looking at here, or we're about to see. So we take a cannula, which is really just a really long syringe, okay, a really long needle. And that needle we will puncture into our bottle and into the container we want it to go into, okay? Then we say, well, we just tip it over and pour. Well, that's not going to work either, okay? For sure, it's going to go too slow. So what we would need to do is now somehow push down on this liquid so that our liquid or our solvent could move up the needle and into our container. Okay? So how do we push down on that liquid? Well, we push down on that liquid with our nitrogen. So our dry nitrogen comes in, pushes, puts enough pressure on the liquid to force it up and over to the other side. Ideally, we would stagger this out a little bit, and we could even run this as a siphon, and it would eventually siphon the solvent across. As we fill liquid in here, though, the volume's changing, and we're going to get a counter pressure, which means we also need to alleviate that counter pressure, and we can do that with a bleed valve, okay, or a bleed syringe. Bleed needle is the word. And so that will help counterbalance the pressure on that. As long as everything's been degassed, as the solvent flows across, if anything, it's pushing gas out. We don't really need to stress about liquid coming or air coming back in. It's a little bit of a rigged system here. Ideally, that bleed would go out into a system with oil in it that would now prevent atmosphere from coming in. So it would now bubble gas through an oil mixture, which then prevents it from being exposed to air. Like I said, it's a little bit of a rigged system, but this does work to transfer our solvent across, and it gets across the primary idea behind what we're doing here. The reaction itself can be very tricky to initiate because of that radical mechanism. So one of the things that we'll do is maximize magnesium surface area, and this is done by either cutting up magnesium strips really, really small, or by using what is known as magnesium turnings or powder. The problem with a lot of those maximized surface areas is that they will react with oxygen very, very quickly. So in a standard research lab where you can store your magnesium away from oxygen, say in an inert atmosphere, easily, it's not a big deal. But for an undergraduate lab, and even then an undergraduate teaching lab, we don't really have that ability. So our magnesium surface area does get kind of corroded with oxygen, and that does limit the effectiveness of the reaction. So what we can do is try and grind on it to break it up a little bit more. We can use scissors to manually cut pieces. In this particular experiment, it worked out okay with the magnesium turnings because I was able to find some clean ones. Other options, we can throw in iodine crystals. Iodine crystals, just standard iodine, I2, are very, very large atoms. They are so large that they can help facilitate the transfer of a single electron from one place to another. So the iodine crystals can help initiate that. I am rather proud of the fact that I've not had to have my students use iodine crystals, and that really we just give it a little bit of heat to kind of push this, look at our magnesium surface area, and give it enough time, and it runs fairly quickly and easily on its own. But one of the problems here is that we have to watch our reaction and make sure we don't heat it too much. Unfortunately, I wasn't watching it as carefully, so I had to back off the heat pretty quickly here.